Okay, our next step is to move on to actual mass stoichiometry. So, working out things that are happening in a chemical, across the chemical equation, the key concept is a thing called mole ratios. It's the way we use ratios to work out, if we know the reactant, how much product we get, and vice versa. So it's using the equation to link up the number of reactants and the number of products. So in that combustion equation that we just balanced, what did we have? We had one propane molecule reacts with exactly 5 oxygens to produce exactly 3 carbon dioxides and exactly 4 waters. So there's always going to be, no matter how much the reaction goes, how much propane burns, you're always going to have 3 times as many carbon dioxides produced as you had propanes consumed. For every 5 oxygens that react, there's always going to be exactly 4 water molecules produced. It's always going to be in those ratios. They're the magic ratios which enable us to work out amounts in chemical reactions. Always those proportions are going to be reacting. And it's the ratios they produce which are critical to the process. So that becomes the mole ratios of the chemicals involved. There is going to be 1 propane for every 5 oxygens, for every 3 carbon dioxides, for every 4 waters. 1 to 5 to 3 to 4. They're the mole ratios. So if we know 1 reactant or product, we can use those ratios to work out the amount of any other reactant or product in that equation. So as we've just been doing, just applying it directly to that equation, 1 mole of propane will produce exactly 3 moles of water and 3 moles of carbon dioxide, 4 moles of water. That means if we double the amount of propane, we'll double the amount of carbon dioxide and we'll double the amount of water. We can work backwards. If we want to produce 4 moles of water, then that tells us we're going to need exactly 1 mole of propane, exactly 5 moles of oxygen. And they don't have to be the exact numbers that we've got in the equation. If we need 10 moles of carbon dioxide, well, we know that there's always 1/3 the amount of propane needed. So if we need 10 moles of carbon dioxide, it's going to be 1/3 of 10, 3.33 moles of propane required. Always going to be in that 1 to 3 ratio. So if we're to get that, ratios can be tricky things, if we're to get that ratio right, it's good to have a set process, a set little procedure to work through to get the mole ratios right. The idea of want over got. So we can do a few calculations based on this equation, the Haber reaction producing ammonia, enabled the development of high explosives in the First World War and blowing up half of Europe. So, applying mole ratios. How much hydrogen is required to produce 5 moles of ammonia? So, we've been given the number of moles of ammonia, that's what we've got. What do we want to find out? We want to know the amount of hydrogen required. So we want to know hydrogen, we've been given, we've got the moles of ammonia. Want over got is hydrogen over ammonia. So we take the coefficients. We want to know hydrogen. Now the coefficient of hydrogen is 3. We've got the moles of ammonia. Coefficient of ammonia is 2. So we use want over got, 3 over 2. And so we'll multiply our number of moles that were given in the question by 3 over 2. That tells us the number of moles of hydrogen required is 7.5. The number of moles given to us in the question multiplied by want over got. Always the same process in any stoichiometry problem. Always think if you've got an equation, you're working out amounts, want over got. How much hydrogen is needed to react fully with 4 moles of nitrogen? Well, what are we being asked for this time? We're being asked for hydrogen. Want is hydrogen. What are we given? Nitrogen is what we've got. Want over got is hydrogen over nitrogen, which is 3 over 1. So we're going to multiply the moles given in the question 4 by want over got by 3 over 1. And that means 4 times 3, of course, which equals 12. Always the same, just want over got. Coefficient of what we're being asked to find over the coefficient of what we've been given the moles of. Of course, we don't usually have whole numbers of moles. We're always going to have decimals, pretty much always going to have decimals. So this time we want to know the ammonia. We've been given, we've got the moles of nitrogen. Want over got, 2 over 1. We want to know how much ammonia. We've got the moles of nitrogen. So, want over got, 2 over 1. Okay, have a go at a few questions on that. It's really important to have a go at these. And if you're struggling to work it out, please get in touch. This is a key concept in calculations in chemistry, so it's an important one to make sure that you get the hang of. Not hard with a bit of practice, but just make sure that you do it.